Hello, this is example 3 from section 8.2. The safeties of those who work at or live close to nuclear plants has been the subject of widely publicized debate in recent years. One possible health hazard due to radiation exposure is an excess of cancer deaths among those exposed. One problem with studying this question is that the number of deaths attributable to either cancer in general or specific types of cancer is small, and reaching statistically significant conclusions is difficult, except after long periods of follow up. An alternative approach is to perform a proportional mortality study, whereby the proportion of deaths attributed to a specific cause in an exposed group is compared with the corresponding proportion in a large population. Suppose, for example, that 56 deaths have occurred among 55 to 64-year-old male workers in a nuclear power plant, and that in 13 of them the cause of death was cancer. Assume, based on vital statistics report, that approximately 20% of all deaths can be attributed to some form of cancer. Is this result significant? So what that is basically saying, because I'm going to do a one prop z-test here, as long as I meet all the requirements. But I'll come back to that issue. What this claim is saying, for it to be significant, that means the proportion would have to be greater than what it is for the general public. So 20% or 0.20. So that's what the claim is. And then our null will be that p equals 0.20. And our alternative will match our claim, so greater than 0.20. That's what significant would mean. Now here they didn't give us an alpha value, so I am going to use alpha equals 0.05 because it wasn't given. But now, before I continue with this question, let's make sure I meet all the requirements. It didn't say a simple random sample, but I said we can assume that one. Does it meet the binomial conditions? Well, they either died from cancer or they didn't. There's a fixed number of trials. People are independent, and the probability of success will remain the same. So we meet the binomial conditions. And then last but not least, are there at least 5 successes and 5 failures? Yes, there's 13 successes and 43 failures. So we can do the one prop z-test. Well, I already got my claim and hypotheses, so the next step would be a picture. And because my alternative hypothesis is greater than, this is going to be a right-tailed test. And like I said, we'll use 0.05 for our alpha. Next, I need to calculate the test statistic. But before you can do that, you need to know what p-hat is, which is 13 over 56. And I'm going to leave that as a fraction for right now. So then our test statistic z is p-hat minus p, and remember p comes from the null hypothesis, so 0.2 divided by the square root 0.2 times 1 minus that, or 0.8, over n, which is 56. So if I go ahead and plug that into my calculator, I'm getting 0.60. That's good for a z-score. I'm going to do the critical value again. So because I need the area to the left to look this up, I need to look up 0.95 instead of 0.05. So go to the table and look up the closest to 0.95. You find that it's exactly in between 1.64 and 1.65, so we get 1.645. Then I look at the 0.6 plot it. Well, 0.6 will be right here. So our decision is fail to reject. The null. So then our conclusion is there is not enough evidence to support the claim that those that work at least at a nuclear power plant experience a higher rate of cancer. Now, the reason why I didn't say live is because this study looked specifically at only people that work in a nuclear power plant, not ones that live near them. And that's it for example 3 of section 8.2.